Hello, hello everyone. I hope you all are here online and yeah, am I audible clearly? Dr. Noor, are you here? Hello. May anyone please respond? Yeah. Great. Thank you. Yes. So, Dr. Noor, are you here? Are you able to hear me clearly? Okay. So I think there is some issue in that side. Okay. So all others who are here, okay, just let me know the things, the major problem where you are facing. Let's discuss first. Then we will move to our next point. Okay, I will go one by one. Shanti Vijay Kumar, are you able to hear me clearly? Yeah. Okay. Yeah. So, Dr. Noor, that yeah, I also cross-checked and I solved these both the problems. Okay, so the answer what you obtain is absolutely correct, and yeah, I will suggest you to write to NPTEL team. So you just mail or either at NPTEL address or either at Professor Kalita's address. So you just mail that your answers are correct, but these correct answers are not uh, listed in those four options. Yeah, is it okay? Yeah, this one is for which? 81.36. We discussed, if I will open the last screen, let me open the file. Yeah, so we were discussing one problem related to flat plate collector. The values for the R not 1 and R not 2 what we are getting is absolutely correct. So, and the second problem related to PV is also correct. So, so do not need to worry much. Just you can write a mail. It will be enough. Okay. So, okay. Shall we move ahead? Okay. So, yeah, Dr. Noor, is it okay? Okay, so let's move to the today's topic, and I'm going to share my screen. Okay, so in the last lecture we discussed a problem related to solar water heater. So how to solve the efficiency and the overall heat losses. Okay, and so in the today's session, we are going to discuss about the solar air heater, the fundamentals of the solar air heater, and then we are going to solve a problem so that we can have a in-depth strength on the various concepts, the losses, the efficiency factors, and all. So we will solve one problem at the last. Okay, so this will be for the today's session. Okay, so this is one thing, and another thing, in the last session we solved a problem related to solar, uh, especially solar water heater. So if you want me to go through that numerical, so I can begin with that also. So let me know what is your point. Shall we start with the solar air heater, or you want to have some glimpse of the solar water heater also? Though the video is available on the YouTube channel also. Okay, so one thing, can anyone tell me the what is the difference between the uh, actual useful energy and the useful energy? How do we calculate these things? How we calculate the overall energy gain or the useful energy gain in a we can take example of the solar water heater or solar air heater. For the both, the system is the same, temperature is going to vary. uh, Ultimately we have to increase the temperature. uh, Let me see. uh, for assignment, 9, have you submitted the assignment? Is the deadline crossed for that? uh, so here in this session, that we cannot solve the same current assignment. What we will do, we will I have prepared the lecture that can cover the concepts of that assignment and the theory you read in the past week. So we will go this way. Okay, so otherwise it won't be justified uh, to solve the assignment here. So we will take example, and then with that example we will try to understand the concepts. So it will be much better, and it will help you to solve other numericals as well, besides the assignment, the numerical given in the assignments. Yeah, so we are talking about the uh, heat gain in a system, how we define, it, and what is the difference between the useful energy gain and the actual useful energy gain. Okay, can anyone make a comment on that? Dr. Noor, Miss Shanti Vijay Kumar is here. Uh, no, no, I'm not asking in terms of the solution. I'm asking the concept, the differences between the useful energy gain and the actual useful energy gain. There are two terms whenever we will come across the heat transfer in a system. So because all the efficiencies and all the efficiencies and the heat removal factors and all other related factors we consider, so there becomes a difference between the useful energy gain and the actual useful energy gain. Actual useful energy gain is whatever we are having at the end side. Okay, so let's move toward the lecture. So we are going to discuss about the solar air heaters. So generally, these systems are for mainly for the thermal comfort, or also used in the industries as well. Uh, if you see the system here, if you see, there are only two things. One is the absorber plate at the bottom, and another is the cover. So the absorber plate, at that side we will having passes for the air, and the air will be passed from one side to another side, and the based on the uh, air flow, type of the air flow, or we can say what the passage, what the channel we are providing to flow the air inside the solar air heater. So we can differentiate it into two or three parts. So yes, if this is the passage for the air, and this one will be our absorber plate, and here we can say one, this is a transparent cover. So it will be like a analogy, it is an schematic for this kind of the system, or this kind of the system. So one, mainly two things are we are having here. One, this one is the glass cover plate, and at the bottom there will be one absorber plate, and others, then we are having the passes for the air and all things. So the basic, if you go to the working principle of that solar air heater, so it is used it uses solar energy to heat the air flowing between the absorber plate and the back insulation cover. That's it only. So ultimate aim is to heat the air and to get a thermal comfort. So in this system, we have to go through some effectiveness parameters that define the effectiveness of the system, that solar radiation intensity, what is the ambient temperature, what number of the glass cover we are using. Mainly one single or mostly two cover system we usually use, and number of the passage and the orientation. Orientation means how we are providing the passage to flow the air. Two main components it has: absorber plate and glass cover, and heat transfer fluid is in the system is air. So again, if we see the classification of the solar air heater, we can classify it as an active, hybrid, and passive system. Means it will come with storage and without storage, and it will be having some PCM storage system also. PCM is the phase changing materials. What happens with the change in the temperature? Uh, the property of the material, specifically the boiling point stage, gets changed, and with that it retains the heat, and whenever necessary it releases heat also to the system. And so it will come with fins and without fins. Fins means, if I see this a normal system, so fins will be there to support the turbulence for the air. So the turbulence will ensure the more heat retention, and then it will be one absorber plate, one will be their cover. So it may not be their cover, but it generally comes with a one cover system or the two cover system, and it may have more than two covers also. Three cover system is also usually read, but in at ground level we will see one cover and two cover systems. And then these systems comes with may come with a solar tracking, means with the movement of the earth, the position of the sun will change. uh, so according to have the maximum solar irradiance on the surface of the absorber plate, so in with the help of the tracking we can change the angle of the solar air heater system also. So these are the basic classification, and then we go toward the solar air heater classification based on the passage of the air. So if we see the air goes from one end and uh, comes out through the another end, so it will be with the help of the circulation. So it will be just a counter flow kind of system, and it may have two types. One is the air inlet is at insulation side, and in the second type of system the air inlet at cover side. In another way we can have when we are not providing this circulation inside the system, so in that case we can have a parallel system. So air will be parallelly passing through uh, the insulation side as well as the cover side. So these are the basic classification of solar air heaters based on the flow of the air or the air passage. But there are two things. The limitations of that means poor heat transfer between the air and the absorber plate, and second thing, the sunlight or the solar energy does not remains throughout the day same, so it may interrupt the efficiency. So the two things comes here to study the efficiency of the system, and the second thing the overall losses of the system. Okay, so let's discuss about the losses in a typical system. So if anyone can comment what type of losses we can have in a solar system, be it a solar water heater or a solar air heater, what kind of losses we can have? So like if I take an example of this as a solar system, so suppose this is a top cover and this is the absorber plate. So what may happen? The solar radiation will fall on the cover. So what happen? Some of the radiation may uh, reflect back. This is the one case out of the system. And what happens inside the system? Uh, the longer the wavelengths will reflect back from the absorber plate to the top cover plate, and then from the top cover plate there may be some losses. So we generally say it as top losses, and additionally at the bottom we are providing the insulation because there might be some losses from the bottom side also. So we are considering the bottom losses also, and then we will be having cover plates. It may be one cover plate. So there, if there is one cover plate, then we will be having the two objects inside this. One is the considerable objects to uh, account the heat losses. So one will be the absorber plate and another will be the top cover plate. And another thing, there might be one absorber plate, one top cover plate, and there might be one more additional top cover plate. So we will be having losses through these bodies. So these we have to visualize the system, and if we can visualize the system, then we can easily solve the numericals also associated with any kind of systems. So first we have to see that what kind of losses can be occurred in a particular system. So let's see first the system itself. Okay, so there are typically two types of systems are thus the system classification based on the absorber plate, insulation, cover, top cover, one more additional cover. The system classification goes to four and five different types. So we will be studying here mainly two type of the system, type A and type B systems. Just yeah. So in the type A system, we are having one absorber plate. Toward the bottom side, there might be one bottom loss classified as UB, and from the top cover side, this is absorber, this is top cover. From top cover side, there might be one another loss. It is as UT, and then we are having the emittance factor for both the systems, the top cover side and the absorber plate. So based on this, we have to calculate the overall losses, the factors accounted with that, and so for that, what we have to see first, the direction of the airflow from cold to the hot side, and the second thing, the direction of the losses, and then what the components are uh, consisted in within the body. So when we are going to calculate the overall heat transfer loss, so we have to compute mainly the H. Okay. So we have to compute mainly the top loss and the bottom loss in the case of the solar air heater system. So H1 and H2 will be the heat transfer coefficients for these two objects, and then there will be one cumulative heat transfer, that will be radiation heat transfer coefficient, that is indicated by HR. So these two functions we have to take into the account. And after that, one thing is the heat transfer coefficient we have to calculate. Another thing we have to calculate is F dash, that is the collector efficiency factor. Uh, Based on that, like we see there is a engine, or the vehicle engine, and any other thing. The efficiency of the engine is not 100%. So because of that, there are some losses, and so we have to account every where the efficiency. So this is the F dash is the efficiency for the collector, and HR is the radiation heat transfer factor. So radiation heat transfer factor is a function of the temperature. Uh, this is a Stefan Boltzmann constant, and so it will be basically a function of the temperature and the emittance of the uh, cover plate or the absorber. So these temperature T1 and T2 are for these two systems, and uh, when the cover plate and the absorber plate, these two systems are very close. So in that case, we can take an average temperature instead of the T1 and the T2. So if I see a thermal network for the heat to compute the losses in a solar air heater system. So this is the absorber plate, this is the airflow, and this is the cover. So what is happening typically? The solar radiation is falling on the cover plate and then to the absorber. So there is a temperature of the cover plate, temperature of the absorber plate. Tf is the temperature of the fluid, and here the fluid is the air, and H1 is and H2 are the heat transfer efficiencies. And so in that case, what happens? So when we make a electrical network for this thing and we take an analogy, so there will be a radiation heat transfer factor also. So we have to compute this all in the system. So this will take to a useful energy gain by considering all these factors. So there will be another kind of the solar air heater system in which we are having two glass covers. So in that case, the formula for the collector efficiency will get changed slightly, and it will accumulate. It will account the overall heat transfer and the heat transfer coefficient for the absorber plate and the cover plate, and HR, the radiation heat transfer coefficient, will be same as for the type A kind of the system. Okay, so this is the very basic things. One, we have to know the how the heat is flowing, how the fluid is flowing, and how all the losses are taking place. So for that, later you can go in detail with the given statement. So Tp is the temperature of the plate, Tc is the temperature of the collector, and Tf is the fluid temperature, and H1 and H2 are the heat transfer coefficient. So if we see H1, so this is the heat transfer coefficient for energy that transferred to the cover glass from the fluid, and the H2, it is with respect to the absorber plate. Yeah. So then we come, so we have to calculate. Okay, if I simply see this system, this as a system, or more clearly, if we simply see this kind of system, so ultimately what we have to calculate? Ultimately we want to know if I am going to install any kind of solar air heater, so what the ultimate useful energy I can have at the user end. One thing that I want to know, and another thing, what why we are installing this system? For the thermal comfort. So what the temperature we can have at the end side. So these two things we have to mainly calculate. So while calculating the useful energy and the temperature, so these are the all the end product or the uh, required at the end side. So for this calculation, we will consider all these the losses and the efficiency factors uh, associated with the systems. So Tc is the temperature of the collector, and the Ta is the temperature, ambient temperature. Tp is the absorber, character of the absorber plate, and the Tf is the temperature of the fluid. So we will make an energy balance around all the components. So these three are the basic energy balance calculations. I'm just showing how we derive the equations to solve the problem. So now there are three unknowns, Tf, Tc, one, the energy difference between the fluid and the collector, the energy difference between the absorber plate and the collector, and the third thing is the energy difference between the absorber plate and the fluid and useful energy gain. So to calculate these factors, we have to solve these three equations algebraically. So by solving these two equations, we can have the equations for the temperature difference between the absorber plate and the fluid, and the temperature difference between the collector and the fluid. Similarly, if we substitute these equation in the equation third equation, Tc minus Tf and Tp minus Tf, if these two values we will substitute here and here, so in that case then we can derive the equation for the useful energy gain Qu. So the basic useful energy gain Qu is F dash S minus UL Tf minus Ta. So what happens, for the simplicity, you just imagine us, you just see the very basic equation what gives about the overall heat transfer coefficient, which discuss overall heat transfer coefficient or the heat retention capacity or the and ultimately gives the useful energy gain. So Q is equal to mcp delta T. We also talk delta T is the difference in the temperature in the system, or we also see when we say about the useful energy gain is equal to UL into delta T. UL is the your heat transfer losses and the delta T is the temperature differences. So then when we account all other losses, then the equation becomes Qu is equal to F dash. F dash is the efficiency for the collector, S minus UL, Tf minus Ta. So the temperature difference between the ambient and the fluid. Ultimately, with the help of the fluid, we are going to influence the thermal comfort. So F dash is the heat, the collector efficiency factor. So it will account the all the losses and the heat transfer coefficient. And simply then, if we say if H1 and H2 are these two heat transfer coefficient are equal, then we can consider this as H, and the equation for the F dash simplifies as 1 plus UL upon H plus 1 upon H into 1 minus HR minus 1 raised to minus 1. So now we know how the values for the H1 or H2 will be given, or if not given, it may be same for the both the condition, then we can consider simply as H. Now we have to calculate the HR, the radiation heat transfer coefficient. So radiation heat transfer coefficient, so as we are saying that it is the radiation heat transfer coefficient, so it will particularly consist the temperature of the components within the system, and the second thing, the related emittance of these components. E2 will be related to the cover plate. So and in this case the area is given. Area we can either consider it for the cover plate or it for the absorber plate based on the equation given. And if what happens if the absorber plate or the cover plate, these two are the very close, so we can, instead of having the T1 and the T2, we can go with the average temperature, and the sigma is the your Stephen Boltzmann constant. So the thing is, simply we have equation Q is equal to mcp delta T or Q is equal to UL delta T, and we are accounting the uh, collector efficiency factor and the area and all heat losses and the heat transfer coefficients. So based on that, we get a simple equation Q is equal to F dash S minus UL and the temperature difference between ambient to fluid, and F dash will based on the heat transfer losses and the heat transfer coefficient. So next we have to derive the equation for HR. HR will be this. And then the thing comes that what will be the value for the H? The value for H depends on the Nusselt number. So Nusselt number, it is basically for the bodies having heat transfer, permitting that heat transfer from one end to another end. So in that case, we have to calculate the Nusselt number, and the Nusselt number, so it will be a function of the Nusselt number and thermal conductivity upon uh, hydraulic diameter. So what can happen? The air passage may be rectangular or it may be cylindrical. So in that case, we have to see the hydraulic diameter. So hydraulic diameter will be 4 into flow area upon wetted parameter. So based on that, we have to calculate the hydraulic diameter. Then next we have to calculate the Nusselt number. So for Nusselt number, we have to see what is the Reynolds number. Actually, we have to see that if it is turbulent or the flow is laminar. So based on that, we will use the formula for the Nusselt number. So if it is the Reynolds number is more than 2100 and the length to the hydraulic diameter, the ratio of length to the hydraulic diameter is large enough. So in that case, the flow will be turbulent. So mostly in most of the problems, we will see this kind of the situation. So in that case, we use a formula for Nusselt number is directly correlated with the Reynolds number. So yeah, so these are the basic things how to calculate the useful energy gain, the temperature of the collector, the Nusselt and the heat transfer coefficients. So let's okay. So for 1 or 2 minutes, we can discuss if you have any problem with the derivations and the formulas, or if it is okay and everything is clear, then we can move to solve the problem then. So are the formulas clear to everyone? Yeah, okay. So in question number T1 and T2, there is air inlet temperature and ambient temperature. Okay, yeah, yes. So you will be having the air inlet temperature and the ambient temperature. So this will, Dr. Note, these two things will help you ultimately to get the collector temperature. So if I will take you shortly to that formula for the collector temperature based on the Fi, yeah. So we will be having the inlet temperature. Based on the inlet temperature, we will calculate the mean temperature for the absorber plate and the fluid temperature, and then we will be calculating the outlet temperature. So this is having a correlation stepwise to ultimately calculate the outlet temperature. Okay, any other thing? And anything else to discuss within the formulas? Okay, so I believe you might be having pen, paper, and calculator with you. Can you please unmute yourself? Dr. Noor, Miss Santi is here, and someone, Mr. Tej is here.
Yes, sir.
Okay, so I believe you are having pen, paper, and calculator with you. If you are having with you, it is fine. If not, I will request you to please just arrange within a 1 or 2 minutes. Then we are going to uh, solve a numerical that will make our understanding more clear on the concepts and the formulas. Okay, so shall we go with the numerical? Tej, I didn't get you. Oh, okay, okay, no problem. You just keep your focus on the slides and whatever we are going to discuss. Dr. Noor and Miss Shanti, are you available with the calculator, pen, and paper? Okay, so great. So, so next in the next slide, I'm going to uh, uh, share a problem. So I will request you to note down it, and or you may take a screenshot also, and then note down all the given parameters, and we will give a time of 2 to 3 minutes for that, and then we will go to solve the problem. Okay, so please note down the problem. We have to calculate the outlet temperature and the efficiency of a single cover type system. So as this one is given, and the most of the formulas we discussed, these were related to this system only. So we have to calculate the outlet air temperature and the efficiency of a single cover type air heater, which is inclined at a slope of 45 degree, and the radiation incident on the collector is 900 watt per meter square. Okay, so one point is given 45-degree slope, and the radiation incident on the collector 900 watt per meter square. The plate to collect cover spacing is 20, this spacing is 20 mm, and the air channel depth is 10 mm. So, and then area and the length is also given, 1 meter wide and 4 meter long. The absorber plate is selective with an admittance of 0.1. So, EP is given here, and the effective transmittance absorbance product. So, this will be tau alpha. Tau alpha is 0.82. The inlet temperature is 60 degrees centigrade, and the ambient air temperature is 10 degrees centigrade is given, and the mass flow rate for the air is 0.056 kg per second. So then the wind heat transfer coefficient 10 watt per meter square degree centigrade is given, and the sum of the back and edgeless coefficients H1 and H2 for that is given 1.0 watt per meter square degree centigrade. The emittance is also given, epsilon 1 and 2 is 0.95. You please note down these numbers. Okay. Dr. Noor, can you tell the steps to solve this problem? What other hidden factors we have to solve, or do we need to take help of some standard correlations to solve this problem? Okay, no issue. So I'm going to take you toward the steps. Shanti, have you noted down the problem statement? Okay. So can you tell me the steps to solve the problem? Whatever the random steps you are having in mind, you may tell, then we can discuss further. Like we discussed few things that we have to calculate the outlet temperature and we have to calculate the outlet temperature and the useful energy gain. So what else we have to calculate to get these figures? Yes. Okay. To find UL. Okay. This is one thing. Okay. So you might be clear with the formula for the UL calculation. And another thing, what we have to calculate. Okay. So another thing we have to, yeah, HR. Yes, correct. Anything else? For the HR calculation, we just need the admittance factor. Yeah, admittance we are having is Boltzmann constant. It is also given, and F dash we have to calculate based on the H, HR, and UL. We will be able to calculate H dash. Sorry, F dash. And besides this, we have to calculate. Yeah. So then, see this slide. We have to calculate the H, and for the calculation of the H or the Nusselt number, we may have to calculate either of them. We may have to calculate either the H or the Nusselt number. So for this, we have to calculate the Reynolds number. So the Reynolds number actually tells the flow is the laminar or the turbulent, and we will check two things. Uh, One is the Reynolds number, and another is the length to hydraulic diameter ratio. If it is more than two, Reynolds number is more than 2100, and length to hydraulic diameter ratio is significantly large. So in that case, we will use the formula for Nusselt number is 0.0158 into Reynolds number to the power 0.8. So this is okay. So these are the basic things. Now, okay. So let's discuss in detail. So ultimately, we have to take. We have to. So there is. If you will follow the standard books, you will get some correlations in the book itself. So suppose this. Uh, we have given the top loss. We have given the slope of 45 degrees centigrade, and plate spacing is given in the numerical slope 45 degrees centigrade, and the plate to cover spacing 20 mm is given. So in that case, if you have to calculate top loss coefficient of the UT, so we can simply take the help of these correlations given in the standard books. So if we take an average temperature of 70 degrees centigrade, so average temperature we are taking based on the given the ambient and the temperature of the absorber plate. So based on this, we are assuming an average temperature of the 70 degrees centigrade. So if you see, uh, and the second thing, this is system is single cover type system. So if you'll see, there are three plots here: one cover system, two cover system, and three cover system. So we will assume for 70 degrees centigrade, we will see uh, the average plate temperature is given 70 degrees centigrade, and we have to identify the top loss coefficient. So this is for single cover. So here we can see, for a single cover at 70 degrees centigrade, if I assume this one as 70 degrees centigrade, so somewhere here we can get a top loss coefficient of 3.3 watt per meter square per degree centigrade. So next we have to calculate Q is equal to mcp delta T. Delta T is the temperature difference between the outlet and the ambient. Outlet means the air is passing through the system, and what will the at the outlet side. So this is a very simple equation, Q is equal to mcp delta T, and if I consider the uh, heat loss and I see a system as a heat exchanger, so in that case we have to consider all the losses through the conduits, and then I can come up with this equation that is correlating all the temperature at the collector, at the ambient, at the sky, and these are the emittance factor and Stemann Boltzmann constant. And another thing, then we have to calculate the efficiency. If once we will having the QU, so efficiency will be QU upon AC GT. So then we will be having we are having the inlet temperature. So based on the inlet temperature, we have to calculate the temperature for the mean temperature for the fluid and the mean temperature for the absorber plate. So fluid is the air. Okay. So once we have calculated the mean temperature for the fluid and the air, then we have to calculate ultimately this is the heat removal factor FR, and F dash we have to calculate, and the correlation will be uh, FR will be the F double dash into F dash. So FR is the collector heat removal factor and FR is the collector flow factor. This is the collector heat removal factor, and F double dash is collector flow factor, and F dash it will be a collector efficiency factor. So based on this, ultimately we have to calculate FR. Once we have calculated the FR, we will keep this in this equation FR, and based on that we will be able to calculate the actual useful energy gain. So that's why I said there are two terms: the useful energy gain QU, and another term is QU. So these are not same. Whenever you will see the numericals and problem or the given uh, figures, so these QU and the QU both are not the same. This is the useful energy gain and this is the actual useful energy gain. Actual useful energy gain will be accounting all kind of the heat transfer coefficients and the heat losses. So this all is for the today's session, and yes, I will suggest you to follow this book for more numericals, to practice more numericals. This is book on, you can note down, solar energy, solar engineering of thermal processes by, so this is by John A. Duffy. So yeah, so the name of the book is in the chat box. You can note down it. and the author name is so you can go through this book, and so this will help you to solve more numericals in such problem. Okay, so is it clear, Miss Shanti, or anything else do we have to discuss? Okay, okay, so with that, we are going to close the today's session. Okay, thank you very much. And the video will be available online, so you can follow again to note down the formulas and all things. Thank you, everyone.